can you please switch on your video so that I
Ma'am,
can...
to maintain the bandwidth, I'll be in offline, I mean, non-video mode. Initially, I could start my video. Okay, ma'am? Sure.
For 5 minutes so that I can introduce.
Sure, ma'am. Sure, ma'am. Am I visible, ma'am?
Yes, sir. Perfect.
Yeah. Okay.
Yeah, we are starting, sir. Good morning, everyone. Welcome to the day 5 of FDP on Nanocomposites and smart materials in aerospace industry. So we have here the speaker for day 5, session 1, Dr. Vairi Vignesh sir, who is having a blend of academic as well as administrative and research experience at a very young age. So Dr. Vignesh is presently working with Amrita School of Engineering, Coimbatore. He is a PhD scholar from Amrita School of Engineering in September 2019. He has a experience as junior research fellow in development, field trials, pilot production, and technology demonstration of sintered brake pads with improved performance for wind tunnel turbine applications suitable to India-specific wind characteristics. Development of laser surface texturing technology for automotive application. He's been also a teaching assistant in the Department of Mechanical Engineering, been coordinator for various events and NAC and all. So he is a recipient of awards like ISTE Chapter Best Student Award, Henry Ford Award from Karpagam College of Engineering, Best Technical Paper Award in the International Conference Emerging Trends in Materials and Manufacturing 2017, and Certified Publons Academy Peer Reviewer. He has been invited for various talks as guest speaker and panel judge at various conferences and webinars. To his credit, he is having a patent on hybrid black toner and virtual reality based wireless rescue robot and a method to rescue child fallen into deep well. Apart from this, his main research, which is oriented towards solid state processing, solid state welding, surface engineering, corrosion science and engineering, tribology, he is having over 59 articles published in national and international journals with citations of about 227 citations in Scopus, 08 H index papers, 6 item index papers, 4 book chapters, 2 Sci index papers, and 15 SIE index papers. So you have a very versatile profile. We welcome you, and I hope your knowledge will be very informative and useful for our participants. And I would like to say that the participants are from a and industry because this is a faculty development program. So students, research scholars, and academics, the background is. So your questions all will be aimed on that. With this brief, I would like to hand over the session to Dr. Vairi Ganesh, sir. Thank you.
Yes. Thank you for a brief introduction about myself, ma'am. Yes. Good morning, everyone. So in this pleasant session, I'll be giving a wide talk on solid state processing and characterization of AZ91 alloy that is reinforced with nanophase silica particles. And myself, Vignesh from Amrita Vignesh-FDP, Coimbatore campus. So to ensure bandwidth, I'll be turning off my visuals right now so that it is easy for everyone to grasp the presentation contents. Yeah. I hope ma'am has given a brief introduction about myself. So I did my BE from Karpagam College of Engineering. Then I have completed a Doctor of Philosophy from Amrita Vignesh-FDP. Then I have started my career as assistant professor from the same institute by 2019. And before going into the topic of today, let me introduce the labs that I am associated with and the facilities at Amrita Vishwavidyapitham in our labs. So I'm associated with friction stir welding lab right from my teaching, right from my career start. And we have established this lab in Amrita by 2016. And we do work on friction stir processing of materials with respect to surface modification and surface compositing techniques. Then we work on similar materials and dissimilar materials, friction stir welding, and friction stir spot welding concepts too. And we do work on Tailor welded blanks. The next lab that I am associated is Materials Processing Lab. This lab is established with support from Amrita Vishwavidyapitham, then Department of Space and ISRO. And we have facilities for working on powder metallurgy of materials, fabrication of ceramic tiles and ceramic polymer pavement blocks. And we do have facility for hot rolling and cold rolling of materials. Besides this research, we do work on vacuum brazing of materials. Dr. M. Govindaraju sir, he is an expert in vacuum brazing of ceramics to alloy, and he has 2 research-funded projects currently live in the lab. And these are the facilities that we have in our lab. First is the friction stir welding and processing setup, immersion corrosion setup with thermostatic bath, continuous casting setup, multi-purpose heat treatment furnace, vacuum brazing furnace, high vacuum brazing furnace, high frequency induction furnace, high rolling mill, ball milling unit, foil rolling unit, and conventional tribometer setup. And these are established with the funds from ISRO, Department of Science and Technology, and Department of Space, and Amrita Vishwavidyapitham. Yes, with this brief introduction, I'm just going into the topics of talk today. So I'll just begin with an introduction to biodegradable implants and the need for implants with respect to magnesium alloys. Then we'll discuss the concept of view on the surface composite concept. Then we will discuss the research outcomes based on AZ91 alloy reinforced with nanophase silica particles. A base introduction to biomedical implants and magnesium alloys. So implants are materials that are engineered to interact with the biological systems. Implants are utilized for hard tissue or bone fracture based things. They substitute and support the functionalities of the damaged bone. Conventionally speaking, these implants are made of polymeric, ceramic, or metallic materials. A few of polymeric materials that is used for implant applications include polyethylene, polyketones, polyacetate, and PGA based derivatives. The problem with this polymeric implant materials is their limited biocompatibility. Next, coming towards ceramic materials, alumina, silica, zirconia, and HAP, hydroxyapatite based ceramic materials are into the picture if we want to have an implant material based on ceramics. But the problem with ceramics is their machinability. And coming towards metallic implant materials, researchers and medical people have been using this stainless steel based, chromium, tungsten, titanium based alloys for implant applications. However, when we check the property of these conventional materials with the bone, which is given over the table over here, we could observe that the density, compressive yield strength, and Young's modulus of these conventionally used metallic implant materials are very much higher than that of the bone parts itself. For example, we could typically take titanium alloys, which is conventionally used as an implant material. We could observe that the density of titanium alloy is more or less twice that of the density of bones. Added the compressive yield strength, we could just see the bone has a compressive yield strength of 130 to 180 megapascal, but the titanium alloys will have around 970 megapascals. Young's modulus 2, when it comes towards bone, it will be 30 gigapascals, and if it is titanium alloy, it is going to be around 120 gigapascal, which is 4 times higher than that of the requirement. So generally people would think, if we are going to place an implant for a fracture based region, so it should have high strength, but it is not the case. When we place a material with high strength or high density or high Young's modulus near a fracture bone, that will cause deteriorating effects too. Okay, so we'll just see the effects of such things in detail. So if we place a material that has undesirably high strength and high Young's modulus, it will create high tendency for the implant material to absorb the stresses that are transmitted to the specific area of the body. Okay, and this will induce a body mechanism to reabsorb the developing bone material, which deteriorates the bone density of the developing bone. And these accretive process, that is the tendency of implant material to absorb the stresses and the induction of body mechanism to reabsorb the developing bone material, will lead to loosening of the implant and bone refracturing. Okay, and this effect is called as stress shielding effect. So it is not desirable at all. Added to that, these implants are always non-biodegradable, which means they will not corrode inside the human body. For example, it can be stainless steel or titanium or any other material. It will not degrade in vivo. So there is a need for secondary revision surgery after bone heals completely. And added to that, since it is a non-biocompatible elements, for example, titanium, stainless steel are not biocompatible elements. So stainless steel in the case, iron and chromium, that is going to be our ions in stainless steel, right? So if they corrode or if they make weird debris, they are non-biocompatible. So that will release toxic ions in the vicinity of the implants that will lead to inflammatory osteolysis, which means there will be non so bad response from the tissues that is surrounding the implants. So these are the negative things when it comes into the picture when we have conventional metallic implant materials with undesirable high strength and high Young's modulus. Okay, so this creates the need for development of materials with good strength equivalent to that of bone and Young's modulus equivalent to that of bone, so that we don't end up with stress shielding effect or inflammatory osteolysis. Yes. And coming towards the biodegradable concepts, and people have been working on this biodegradable concepts right from 1850s, and these biodegradable implants should have the inherent ability to corrode in human physiological environment. Generally speaking, we'll see the graph over here. Okay, so the strength or intactness of the implant regenerating bone over a period of bone healing period, it's shown in green color trend line. So at the instance when the bone is fractured, it will have 0% strength, and when it reaches the complete state, it is going to have 100% strength. So that is going to be my relative period. So I am just considering this right now. So if I place a conventional implant that has high strength than that of the regenerating bone, obviously we'll end up with stress shielding effect. But in case if we could develop a biodegradable implant, okay, so that will have the trend line as shown in blue colored one. So what happens is during the implantation period, the implant will just dissolve into the human body. But the problem with the currently used biodegradable implants is they just prematurely fail before the bone heals completely. Okay, so we have to develop a bone material that has an elongated period of time for uh, dissolution, so that the bone healing period of this regenerating bone and the proposed biodegradable implant to dissolve into body meets at an exact point. Okay, so this is what we have to do. So we have to ensure that the proposed biodegradable implant will have gradual loss in material and mechanical strength during the degradation process, and that has to be balanced. by the increasing strength and stability of the newly forming bone. And added to that, the biodegradable implant should also support tissue regeneration and healing by dissolution, resorption, and formation of corrosion products that enhance osteoconductivity. So it means that the cells which is near to the bone and the implant should consider that bone implant material as its own thing, and it should develop a habit of forming new tissues near the implant material so that we'll get healing period somewhat in a lesser time. Okay, yeah, fine. So this is the requirement of biodegradable implant. One is extended period of healing period, and second is supporting tissue regeneration and healing by dissolution, resorption, and formation of corrosion product that would enhance osteoconductivity. So these are our requirements. So when we consider these factors coming into the picture, magnesium will have many advantages over any other conventional materials. The first is the density, compressive yield strength, and Young's modulus. First, let me go ahead. First is the density, compressive yield strength, and Young's modulus. And why? Because the density of human cortical bone and the magnesium alloys are very similar, and the compressive yield strength and Young's modulus are going to be very similar to that of the magnesium alloys in most cases. Added to that, this equivalent compressive yield strength, Young's modulus, and density will give us only marginal stress shielding effect if it is implanted in the human body. Added to that, magnesium has inherent ability to corrode in the human physiological environment, which is rich in chloride ions. And even if this magnesium goes into the body, this will create magnesium ions, and that will these magnesium ions are cofactor of more than 325 enzymatic reactions within the human body. That will ensure proper functioning of internal organs too. Added to that, the serum magnesium levels will be maintained by dynamic absorption and equilibrium mechanism of magnesium ions by the normal human body functions itself. Added to that, the World Health Organization also recommends a daily intake of 280 to 300 milligram of magnesium-based salts for adults and 250 milligram for children too. So these factors make magnesium alloy as one of the candidate material for bioimplant applications. And it's a mini bite, and by the year 1878, Edward have tried out pure magnesium implant over a human for a bone fractured human, and the results are just like astonishing. He has found that magnesium is biocompatible, but the problem with magnesium is its high activity that will lead to accumulation of gases near the implant materials when it corrodes. Okay, so that will lead to some sort of lethal phenomenon. So that is one of the major findings of Edward. So that led us to research towards biodegradable implants with controlled corrosion kinetics in magnesium alloys. Yes. And the challenges of magnesium alloys with respect to bioimplant applications is its HCP structure. The HCP structure limits the workability of material. As we all know, the slip systems with this HCP is very much limited, so the workability is obviously limited with this magnesium alloys. And added to that, it is a highly active metal that results in high corrosion rate, and the low density of the material will result in high wear rate too. Obviously, we know magnesium has density of around 1.7 gram per cc. Okay, and coming towards the corrosion perspective, magnesium alloys corrodes rapidly at a pH of around 7.2 to 7.4, which is the pH of physiological fluids, at the rate of 4 to 8 mm per year. But the recommended corrosion rate for biodegradable implants is around 0.5 mm per year. Okay, and if this happens at a corrosion rate of 4 to 8 mm per year, that will result in accumulation of hydrogen gases in the tissues, which is a lethal phenomenon. So we need to develop a process or a composite that will engineer the corrosion properties of the materials. And the bioimplants recommended corrosion rate is less than 0.5 mm per year. That is what I said. So we have to develop a process or composite to engineer the corrosion properties. So the limitations with these magnesium alloys has also to be considered while we choose a process or when we plan for fabrication of a composite material. So among the magnesium alloys, my research topic will include AZ91, which is a magnesium aluminum alloy system. Why? Because earlier researchers have shown that this specific grade of magnesium aluminum alloy system has good biocompatibility and corrosion resistance in vivo environments. Added to that, the it's in vivo animal studies, in vivo based corrosion rate experiments indicated that the corrosion rate of AZ91 is less than the in vitro corrosion rate, which is based on some cell culture based experiments. So in this study, we have taken a wrought AZ91D alloy of thickness 4 mm, whose composition is just given over here. So AZ91, as you all know, it is magnesium 90% and around aluminum, it is going to be around 9% and zinc 1% approximately. So this is the spectrometer readings that has shown me the composition of wrought AZ91 alloy that is purchased from the market. So we are going ahead with fabrication of composite using this material. And let us see the phases that is present in this magnesium aluminum alloy system so that we can come to a conclusion how it could be done or what are the parameters that we should consider while we fabricate magnesium aluminum based system for surface composites. So the first thing is the solubility of aluminum in magnesium is very much limited, and we can see that from the phase diagram only 11.5% of aluminum dissolves at eutectic temperature. And what happens is, beyond this solubility limit, magnesium 17Al12, a brittle intermetallic precipitates come out of the alloy, and that is thermally unstable too. And coming towards the corrosion perspective, the alpha magnesium, which is the primary phase of the alloy, has corrosion potential of minus 1.81 volt against standard calomel electrode in Hank solution, and the beta phase, which is the secondary intermetallic phase that is present in AZ91 alloy, has a corrosion potential of minus 1.08 volt against standard calomel electrode in the same Hank solution. So when we have two phases that is present in the matrix with wide gap in corrosion potential, this will lead to galvanic coupling effect that and in turn that will lead to intergranular corrosion effects too. So we have to ensure that the intergranular corrosion effect is minimized while we fabricate surface composites too. So we have to consider this point of view also. Added to that, why we are saying this is active phase have high tendency to lose electron than the passive phase, that will result in high corrosion rate. So we have to engineer this parameter also so that we get a desired corrosion rate of less than 0.5 mm per year. And here is the list of challenges that is posed by magnesium alloy AZ91 for us towards the fabrication. So first is its activity. So since magnesium based alloy, it is going to be highly active and it will result in intergranular corrosion and microgalvanic corrosion too. And coming towards its soft matrix and HCP structure, it is prone to high wear rates. Added to that, the HCP structure restricts the deformation of the alloy too. And coming towards tensile behavior, it has a soft matrix, and this soft matrix grain size will determine the tensile strength of the alloy. So if we want to improve the tensile characteristics, obviously we have to opt for grain refinement techniques too. Okay. And coming towards biocompatibility, that is a plus point for us because magnesium is second most element in the human body, and it happens like excretion. If it is in excess, will be through some body fluids. Okay, and when we combine these two factors like tensile and corrosion, that is going to be our stress corrosion cracking, corrosion and wear, that is tribo corrosion, tensile behavior and biocompatibility that comes with stress shielding effect, and so these all characteristics are dependent on the microstructure of the alloy, which consists of alpha phase and beta phase. Alpha phase is primary phase of AZ91, that is alpha magnesium, and the beta phase is an intermetallic of magnesium and aluminum in the alloy itself. Okay, so if we can engineer the micro constituents of this alloy, obviously we can get a good resultant. And we'll discuss on the solid state processing technique, that is a friction stir processing technique to fabricate surface composites out of magnesium alloy AZ91. So coming towards friction stir processing, it is a solid state processing technique. Why? Because we process the material well below its melting point of the materials. So added to that, it is a green process too. So in this process, what we do is we just what to say, traverse a region of material where the material is being have a friction stir processing, and there is a
Hello, sir, you're there? Hello?
yeah. I was muted actually. Yeah, am I audible right now?
Yeah, you are.
Yes, ma'am. Yes, can I go ahead with this FSP?
Yes, yes, sir.
Yes, ma'am. Yes, ma'am. So the disintegration and partial dissolution happens. Why? Because there is recovery and recrystallization phenomenon that is taking place in the material. Yeah, and coming towards the recovery, recrystallization, and grain growth process that happens in FSP, we can differentiate it into three zones. One is exactly beneath the FSP tool, that is going to be dynamic recovery, dynamic recrystallization, and grain growth. And the zones which is ahead and behind of FSP tool will be subjected to static recovery, static recrystallization, and grain growth phenomenon. Okay, so generally speaking, materials working process could be classified as hot working and cold working process. In hot working process, the grain structure refinement will be through heat input, and in cold working process, that will be through strain. And in hot working process, dynamic recovery and dynamic recrystallization takes place, and in cold working process, static recovery, static recrystallization takes place. But FSP is unique. Why? Because we introduce heat and strain into the matrix simultaneously, so that there is dynamic and static based recovery and recrystallization phenomenon taking place in the material simultaneously. Okay, and this is the greatest advantage of this FSP process. So we'll be using this process to fabricate surface composites out of magnesium alloy using nanophase silica particles. And even before that, we'll just discuss the properties of base material, that is magnesium alloy AZ91D. Yes. Coming towards the microstructure that is observed under a normal microscope, we could see alpha phase and beta phase in the alloy. So alpha phase could be observed as bright region, and the beta phase is observed as dark region in the optical microscope after etching phenomenon. And we have done some XRD analysis to confirm the phases that is present in the matrix. XRD analysis result confirmed that there are only two predominant phases that is present in AZ91 alloy. One is alpha magnesium, which is the primary phase, and second is the intermetallic phase between magnesium and aluminum, that is beta magnesium 17 Al12. So these are two phases that is present in AZ920 alloy, and the micro hardness of this alloy in the as fabricated status around 57.9 HV. That is Vickers hardness of 57.9 HV. Then for performing immersion corrosion test, we have followed ISO 10993-15 standards, where we have to simulate a normal human environment and we have maintained a temperature of around 37 plus or minus 0.1 degrees Celsius. The corrosion test was done for a period of 7 days. And after performing the corrosion test, uh, the corroded specimens were cleaned using chromic acid with concentration that is given over here. That is, we have mixed 100 grams of chromium oxide in 1000 ml of distilled water, and then we have prepared chromic acid. So that was used to remove the corrosion products over the surface of the material. So initially speaking, the corrosion rate of the material increased to 4.37 mm per year after the first day of corrosion. And what happened is, with increase in immersion time, the corrosion rate of the material stabilized at around 1.05 mm per year after 144 hours of immersion, that is after 6th day of immersion. So we could generally see that the corrosion rate of the biodegradable implants. So obviously we have to go for a process to engineer the corrosion rate. So that is what we have concluded over here. And added to that, we have monitored the pH of that solution with a sensitivity of plus or minus 0.01. So it is found that the hydrogen ion concentration decreases with increase in immersion time. Okay, so H plus is going to be a minus log of H plus, so it decreases with respect to time. So this has to be monitored too when we have to implant the material inside a human body. Why? Because generally speaking, human bodies have an average pH of 7.2 to 7.4. If it goes well below or well high above it, that is also going to be a major drawback if we implant such type of materials. Okay, so we thought of understanding the corrosion mechanism that is present in the material. So we have done some EDS and SEM and XRD based analysis. So initially, after the first day of immersion, we have observed a cracked surface which widened with immersion time in magnesium alloy. That is a normal magnesium alloy. Added to that, we have observed flower-like clusters that bloomed over the surface of the specimen with increase in immersion time. So you can just see A is after first day, B is after 3 days, and C is after 5th day, and D is after 7th day. So initially flower-like clusters bloomed over the entire surface, then it just eventually fell off from the surface. That is, it just dissolved into the solution completely after 5 days. And then after 7th day, there is a complete formation of corrosion product layer over the specimen that is immersed for 7 days. So we thought of analyzing the corrosion products first. So we have taken some EDS analysis first. So the EDS analysis confirms that the corrosion product is rich in elements of magnesium, sodium, calcium, phosphorus, chlorine, and oxide. And added to that, specifically the calcium to phosphorus ratio of these corrosion products changed from 2.15 initially towards 1.65 at after 7 days of immersion. So why I'm speaking this calcium to phosphorus ratio is that this ratio will give us an idea whether hydroxyapatite precipitates over the surface after immersion or not. Why? Because this hydroxyapatite is a mimic of the bone material. So if this hydroxyapatite completely splits over the surface, it will enhance osteoconductivity too. Okay, so this base material, we can conclude that since there is precipitation of hydroxyapatite based crystals over the surface, the magnesium alloy is deemed to be osteoconductive and biocompatible too. So added to that, previous studies have given us idea that if hydroxyapatite is formed over the implant material, that will support bone growth and implant bone integration. Why? Because it is the natural constraint compound of the human bone. And we have done XRD analysis to confirm if this phase is particularly hydroxyapatite based one. Yes, of course. So the XRD results also confirm that the specimen after period of 7 days exhibited the formation of calcium hydroxyapatite and calcium magnesium based hydroxyapatite crystals too. So this is one of the thing that made us to go towards improving the corrosion resistance of this AZ91 alloy through some reinforcements. So breaking down the corrosion mechanism, it is just given over here. So the material, once it is immersed in the uh, normal human body solutions, it will develop a layer of magnesium oxide. Okay, and this magnesium oxide will be converted into magnesium hydroxide. Why? Because it is present in an aqueous solution. So the dissolution of magnesium ions and formation of magnesium hydroxide takes place, and this magnesium hydroxide is going to be very active uh, compound. So what happens is this will act as a potential barrier to absorb calcium and phosphorus. Okay, and why it so is this magnesium hydroxide will react with chloride ions that is present in the DBPS or Dalbecos phosphate buffered solution that we have created to mimic the human body environment. So this chloride ions will be attracted towards this magnesium hydroxide, so it reacts to form magnesium chloride, and this magnesium chloride just goes into solution. Why? Because it is just a highly soluble salt. And after that, what happens is this magnesium has more amount of uh, phosphate and calcium based calcium ions. Okay, so it has more access to phosphate ions and calcium ions. So next what it forms is this forms flower like clusters. So those flower like clusters are just phosphate salts of calcium and magnesium, and these phosphate and salts are nothing but the hydroxyapatite crystals. Okay, so the formation of such crystals over a period of time, that is after 7 days of immersion, it confirms that there is an adherent layer of corrosion products based on calcium hydroxyapatite or calcium magnesium phosphate layer, which is very much essential for implant based applications. Okay, yeah, so this is how the big picture is. So once we immerse magnesium alloy into the body, what happens is there will be formation of magnesium oxide layer. Then because of an aqueous environment, magnesium hydroxide forms. Magnesium hydroxide, it is very active, so it reacts with chloride to form magnesium chloride. This magnesium chloride goes into solution because of its high soluble nature. Then what happens is because of the high accessibility of magnesium with phosphate and calcium elements that is present in human body or this Dalbecos phosphate buffered solution, what is going to happen is it is going to form calcium hydroxyapatite crystals or calcium magnesium phosphate based crystals. So this will enhance the osteoconductivity also. But the corrosion rate of this specific alloy is around 4.37 mm per year, which is not recommended. So that is why we have to go for process that will engineer the corrosion rate of this material specifically. Yes, and we do have done electrochemical corrosion test to assess the corrosion rate and corrosion potential of this material. So this thing I'll be detailing with respect to AZ91D silica based composite in detail. So in this process, what we have done is we have taken the base material, we have immersed it in an SBF solution, which is Dalbecos phosphate buffered solution to mimic the human body environment. Then the temperature was maintained at around 37 plus or minus 0.1 degrees Celsius. We have used platinum foil as our counter electrode and standard calomel electrode as our reference electrode. Then we have done potentiodynamic polarization test. And from that we have obtained corrosion potential and corrosion rate of these specimens. So the characteristics of this anodic and cathodic part will be detailed when we discuss this composite. Okay, so from this also we come to a conclusion that the corrosion rate of the specimens with this electrochemical corrosion test is around 4.49 mm per year, which is very close to the immersion corrosion results too. So this is the basic results that is from base material, that is AZ91T. So from this we'll be going towards AZ91D plus nanophase reinforced nanophase silica reinforced alloy. Okay, yeah, in the upcoming presentation slides. So we'll be discussing on surface composite, that is AZ91D, reinforced with nanophase silica particles. And before going into the topic, let me just give a brief introduction about this composite. The highlights of this composite include grain refinement in the friction stir processed zone. Second is fine dispersion of nanophase silica. Third is the corrosion resistance of magnesium alloy has improved to a great extent. Fourth is the unique surface morphology after corrosion phenomenon that has significantly contributed towards corrosion resistance of the material. And fifth is biocompatible corrosion products, which is very similar to the thing that we have discussed already. Okay, and in this we have fabricated a surface composite. So a surface composite is one that has reinforcement rich layer to the top, and it will have somewhat gradients towards the bottom, and at the bottom it will be completely bulk matrix, that is AZ91D. Yes. So from here we'll be discussing on the fabrication of surface composite. So we have taken a workpiece of dimension 150 by 50 by 4 mm, and we have made a rectangular groove of 150 by 1 by 1 mm on the surface exactly at the middle, and that groove was filled with nanophase silica particles, and it was compacted using mechanical pressing techniques. Then we have done a sealing pass. So in the sealing pass, what we do is we take an FSP tool without a shoulder, without a pin. Then we just insert it over the surface so that it will inhibit the scattering of reinforcement particles when we exactly do the friction stir processing. Okay. Then what we have done is we have plunged the tool inside. Then after a dwell time of 30 seconds, FSP trials were carried out. The consecutive passes were done. For example, if I'm going to do one pass or two pass, it was done after a period of 60 minutes. So let's see the macro structure results over here. So here we have done around 8 experiments to optimize the parameters. One is the tool rotation speed, and second is the tool traverse speed. So specimen A, which is shown over here, which is CM01, it was processed at process parameters of 750 rpm and 40 mm per minute for a single pass. In that, we have observed fill defects and wormholes too. In case of CM02, which was processed at around, in case of specimen 03, we have observed flash and fill defect and wormholes in the material. You can observe all these defect features in the macro structure that is given over here. And the CM04 had flash hole and wormhole, which was processed at 900 rpm and 40. They too had defects related to wormhole and fill defect based. Okay, and when you process the same material at 900 rpm, 20 mm per minute, and for 2 passes, we have not observed any defects internally and externally too. There were no flash, and there is no fill defect, and there is no wormhole. So that picture is shown as G over here, where we could observe there is no defect that is present in the material in the lateral section and in the longitudinal section too. Okay, yeah. So with this, we confirmed that the optimum process parameters for fabricating surface composites out of AZ91D of 4 mm thickness is 900 rpm as tool rotation speed, 20 mm per minute as tool traverse speed, and for 2 passes. Okay, yeah. So with this, we'll just move towards characterization of microstructure. So in the specimen CM07, we could see the stir zone, thermomechanically affected zone, and the base material zone. The TMAZ has equiaxed grains, and very fine grains. That is all because of recrystallization phenomenon. So this recrystallization is attributed to the pinning effect of nanophase silica particles. Why? Because these nanophase silica particles nucleated magnesium grains during recrystallization phenomenon, and it also restricted the growth of recrystallized magnesium grains as indicated in the existing literature. So these are the things that made the material to have a refined grain structure, that is with low average grain size diameter, And second is we had completely dispersed beta phases. So that was observed under transmission electron microscope. So the results are given in the next slide. We could just see it over here, the images right from high resolution transmission electron microscopy. Here we could just observe the grain boundary, partial dislocations and dislocation tangles that is present in the material. So we could literally observe the nanophase silica particles and submicron beta phase particles that is present in the matrix in a completely dispersed manner. So friction stir processing has helped us a lot in breaking and fragmenting this beta phase network and ensuring that we have subgrain formation too. So this subgrain formation is very much essential for improving the mechanical properties of the material. And added to that, we have observed a spot diffraction pattern of the phases that is present in this uh, composite. So the spot diffraction pattern over here also confirms that the region which is bright, that is magnesium, and which is very small over there, that is going to be my nanophase silica. That was confirmed using this spot diffraction pattern. And submicron beta phase particles is also observed, and it is confirmed through this spot diffraction pattern too. And these partial dislocations could be observed from the figure at the rightmost corner, bottom rightmost corner, and we could observe the dispersion fashion of the silica particles and submicron particles in the grains too. So from this we can conclude that friction stir processing has completely disintegrated the beta phase in the matrix, and it has ensured formation of subgrains. So that will lead to improvement in mechanical properties also. Okay, yeah. So we have, in addition, we have confirmed the dispersion fashion through elemental mapping also. So the elemental mapping also confirms that silica, which is shown as blue colored images over here, you can just see it is completely dispersed in the matrix, and SiO2 oxygen in the sense silica and individual map of oxygen also confirms that it is completely dispersed in the matrix. We have done XRD analysis to confirm the presence of silica. So that also confirms that nanophase silica is present in the composite material. Okay, so we have confirmed the grain refinement through microstructural analysis, through a normal microscope, transmission electron microscope, and XRD analysis too. Yes, coming towards the composite hardness. So the base material hardness was around 57.9 Hv, but in the case of composite, in this test zone, the composite had an average micro hardness of 75 Hv. So this attests the ability of composite to resist plastic deformation, and this is attributed to the presence of nanophase silica particles that will act as barriers towards dislocation motion. Okay, so that is why we have got somewhat better hardness in the stiff zone of the material. Okay, yeah, fine. And thermomechanically affected zone, because of the presence of elongated grains along the certain direction, that resulted in minor drop in microhardness values too. Yes, so with this corrosion perspective. So when we compare the corrosion rate of the normal alloy and the composite, the normal alloy had a corrosion, composite had an average corrosion rate of 0.65 mm per year after 3 days of immersion, and after 7 days of immersion, the corrosion rate of this AZ91 alloy has reduced to around 0.26 mm per year. Okay, and when we have observed the surface morphology under scanning electron microscope, we have observed that the number of cracks that is present in the composite is fewer than that of the conventional base material, and the cracks were very narrow with respect to the base material too. Added to that, the cracks have propagated and widened relatively in both the specimens, whether it can be base material or in composite too. And the corrosion products has lesser volume in AZ91D, but the corrosion products were more in this case of AZ91D silica based composite. The distribution of the corrosion products is scattered in case of base material AZ91D, but in the case of composite, it is uniformly covered. Added to that, the structure of the corrosion product has changed right from the base material towards the composite too. In the case of composite, we had clusters of corrosion products. So we can just compare the surface morphology of the corroded base material and composite specimen over here. So immersion period of 3 days and immersion period of 7 days is just given for reference. We could literally see that after 7 days of immersion, composite specimen has uniform spread of corrosion products over the entire surface. Whereas in the case of uh, normal base material, that is AZ920, we had only limited dispersion of corrosion products too. So that is why we had high corrosion rate in this case of magnesium alloy. But in case of this composite, because of the uniform formation of corrosion products, which is adherent in nature, that has limited the corrosion rate of the materials with respect to time. Okay, so these are the factors that have attributed towards the corrosion resistance of materials with increase in immersion time. So the corrosion products play a vital role in determining the corrosion rate of the materials too. So to analyze the corrosion products, again we have gone for elemental mapping and XRD analysis and EDS too. So the EDS analysis has given us an idea that the calcium to phosphorus ratio is around 1.65. So which means there is the formation of calcium hydroxyapatite crystals or calcium magnesium phosphate crystals in the material after 7 hours of immersion. And XRD analysis also confirms the presence of hydroxyapatite in the corrosion products of the material, of the composite material. Yes, and coming towards electrochemical corrosion characteristics, uh, we'll just compare the base material and that of the composite one. So the red colored line is the potential dynamic polarization curve of the base material AZ920, and the blue colored line is the potential dynamic polarization curve of the composite material. So speaking about the cathodic characteristics, the base materials and cathodic kinetics and the composites cathodic kinetics is very much analogous. It is very much similar. So it means that there is minor effect or minor influence of nanophase silica particles on the cathodic kinetics of material. However, when we look upon the anodic dissolution characteristics, there is significant difference between the base material and the composite that we have developed. So in the case of AZ91D base material, once the corrosion potential is higher than that of the the potential is higher than that of the corrosion potential, what happens is there is an exponential increase in current. So which means the anodic dissolution rate of magnesium is very much higher in base material. But in the case of composite, when we have a potential which is very much higher than the corrosion potential, which is denoted as ECAR, we have a pseudo passivation tendency. We could literally observe there is a more or less a horizontal line beyond which there is an increase in uh, corrosion current of the material, current of the composite. So this indicates that the composite has partially protective corrosion product film right between minus 1.30 volt and minus 1.145 volt. So beyond this 1.145 volt, there is a complete breakdown of the anodic dissolution of magnesium. Okay, and this pseudo passivation tendency is lagging in this base material, and in the case of composite we have a pseudo passivation tendency. That means that there is a adherent layer of corrosion products that is forming in the material. Okay, and when we speak about the corrosion potential of the materials, that as uh, as received material, that is base material AZ91D had a corrosion potential of minus 1.448 volt, and the composite had a corrosion potential of minus 1.466 volt. So it means AZ91D is nobler than the composite material, but the corrosion rate, which is determined by the corrosion current, is 3.56 times lesser than that of AZ91, which is a contradicting result. So we thought of analyzing the surface using atomic force microscopy, AFM technique. So we have done some surface potential analysis using this AFM probe. So this is explainable basis explained basis on intrinsic electrochemical behavior of the material, which is influenced by the electron work function. Okay, and this electron work function is the minimum energy required to extract electron from the subsurface of the material without the use of kinetic energy. So when we have observed the surface potential, so of the magnesium and silica, it is observed that generally, this is based on the literature data, magnesium has an electron work function of 3.6 electron volt, and silica has an electron work function of 4.8 electron volt approximately. So when we have low EWF, there is high tendency of electron to take part in electron reactions or chemical reactions. But in the case of AZ91D silica composite, we have finely dispersed silica on the surface. So this retards the anodic dissolution rate of magnesium. Therefore, the corrosion rate of AZ91D silica composite is lower than that of the base material. So here is the result of this AFM analysis. We have done this using Kelvin probe microscope. So X and Y axis gives us the region on which we have done the analysis, and the Z axis just gives us an idea about the surface potential of the material. We could obviously observe there is huge difference in surface potential of the material with respect to the distance. So if we have a high surface potential, it means that the electron reactions will not take place on that region. So from this, we could literally observe that surface composite, because of high surface potential characteristics, it has high corrosion resistance too. Okay, yeah, fine. So when we have observed the same surface under scanning electron microscope, we have observed unique features in the corroded regions. So we could just literally see the formation of star-shaped cluster products, that is also a corrosion product, and bubble-shaped corrosion products in this scanning electron microscopy. So those all attributed to the formation of corrosion products within the surface of corrosion. So that has limited the corrosion rate of the materials with respect to increase in immersion period. And added to that, when we see a conventional material of AZ91D that had very crust and rough features, and there is low, what to say, the features for corrosion products is very much lesser with respect to the composite that we have developed. So from this, we could conclude that AZ91D silica composite is one of the effective materials for biodegradable implant applications. So here is the process window for fabricating composites. So one is we have to process the material at high tool rotation speed and at low tool traverse speed to ensure good defect free region in the friction stir processed zone of composites too. Okay, yeah, fine. So here are the brief outcomes of the research. We have fabricated the surface composite using nanophase silica on the surface of AZ920 by friction stir processing techniques. So the metallurgical characterizations demonstrated that the presence of refined grains, fragmented beta phase, and homogeneously dispersed nanophase silica particles have improved the mechanical and corrosion properties of the materials. And the refinement of grains is attributed to the capability of nanophase silica particles to nucleate magnesium grains during recrystallization phenomenon and to restrict the growth of recrystallized magnesium grains. The corrosion test results indicate the formation of adherent layer of calcium hydroxyapatite and calcium magnesium phosphate layer that reduces the corrosion rate of the material. Cumulatively speaking, we could say that this composite is an effective material for bioimplant applications. Yes. So the session is open for questions right now. If faculties have any doubt or any suggestions towards this case study or research, you could continue.
Request to raise your hand so that we can unmute you. Or you can unmute yourself and answer and ask the questions to Vignesh sir. Srinivas Rao sir, you are having any question?
No, madam. Hello, sir. Sir,
Yes, sir.
good morning, sir. This is Dr. Madhusudan speaking.
Yes, sir. Please
Sir,
go
what
ahead.
is the methodology you have followed in fabrication, sir?
So the methodology is friction stir processing, sir, which is a solid state processing
Okay,
technique.
FSP. Okay.
FSP,
Can
yes, sir.
we have an alternative method, sir, for the fabrication of this?
Yes, sir. There are wide methodologies available for fabrication of surface composites of magnesium, of which this solid state processing technique is good. Why? Because magnesium has a high reactivity in
Yes,
liquid
sir.
state.
Fire,
So
catching
it's
fire.
better to process at solid state processing. Yes, sir.
Catching fire.
Yes, sir.
Any more questions? Okay. So I think there are no more questions with the participants. Hello, Vignesh sir.
Yes, ma'am. Please go ahead.
Yeah, I think there are no more questions with the participants. So, on behalf of MLR
Okay.
Institute of Technology and MLR Institute of Technology, I thank you wholeheartedly, sir, for taking your time out. And also
Thank
the
you.
participants, you are from a different area. This online platform has made it easy actually to
Okay.
share the knowledge.
Yes, of course. Yes. And once again, I thank MLR Institute for giving me an opportunity to showcase my results of work. Yes. Thank you, ma'am.
Sir, Dr. K. Navinalata is asking for analysis which software we need to use.
Yes, specifically speaking for analysis, we have wide softwares for TEM analysis too. We have crystallographic based software for analyzing the spot diffraction pattern. But in case if we are going with corrosion based software analysis, we can go ahead with MATLAB for calculating the corrosion resistance and potential of materials.
So, any more questions?
అని ఏమో నా అంత పొద్దున్న రాడు మామూలుగా టీ కూడా తాగినట్లా
So, good morning, sir. Kishore Nath, sir. I think you are in the session.
I'm repeating this point. Non-editing teacher act as the assistant to
I don't understand. So, convey my regards on behalf of Principal Dr. K. Srinivas Rao, sir, and our HOD, Dr. Satyanarayan Gupta, sir, and also Vivek, sir, for allowing us to share your knowledge. Thank you very much,
Yes.
sir, Vignesh, sir.
Yes.
So, for
Thank
the
you, ma'am. Thank you.
So for the information of the participants, the feedback link has been posted in the chat window. You please fill the feedback form And the next session starts at 11:45 with Prakash Jadhav, sir. The participants can stay back, keep yourself muted, and you can carry on with your work. We'll again meet at 11:45. The YouTube link is also available. If any of the participants have missed with the whole session, you can watch the session in the aerohod channel, official channel.